With current technology, a spacecraft would need more than 70,000 years to travel to the nearest star, a period longer than all of recorded human history. Which raises the question, will we ever be able to leave our solar system? This prospect raises questions about whether we can overcome the immense distances of interstellar space, or if we are confined to our solar system, able to see the stars but never reach them. The answers exist at the convergence of scientific knowledge and imagination, and it is worth exploring how close we are to achieving this goal. Far from Earth, beyond the orbits of Neptune and Pluto, is a quiet region where the sun's influence ends, marking a critical transition in space. Hear the solar wind. A continuous flow of charged particles from the sun decelerates and merges with the interstellar medium, a thin mix of gas dust and cosmic rays that occupies the space between stars. This boundary, known as the heliopause, defines the edge of our solar system's dominion. Closer to the sun, the solar wind moves outward at supersonic speeds, forming a protective bubble around our solar system called the heliosphere, which shields us from some of the harsh radiation of deep space. As this wind travels outward, it encounters the pressure of the interstellar medium and slows down dramatically at a point called the termination shock, creating a vast region of slower heated particles. Farther out, it reaches the heliopause, the point where the sun's wind can no longer push back. For many years, this boundary was purely theoretical. Since no spacecraft had crossed it, scientists could only model and estimate its location, leaving it a mystery. This changed with the Voyager 1 and Voyager 2 spacecraft, launched in 1977. These probes were designed to explore the outer planets, but continued onward after completing their flybys. Coasting on momentum and powered by small nuclear batteries, they ventured into the unknown, becoming humanity's slow-moving envoys to the stars. Voyager 1 was the first to reach the heliopause. There was no photograph or sudden alert to mark its crossing of this invisible frontier. Instead, the evidence came from its instruments. The cosmic ray detector provided one of the first signs. The heliosphere contains lower energy particles carried by the solar wind, while interstellar space is filled with high-energy cosmic rays from exploding stars. As Voyager 1 approached the boundary, scientists observed a sharp drop in solar particles and a corresponding rise in interstellar cosmic rays, indicating a change in environment. Another instrument, the magnetometer, recorded a sudden shift in the magnetic field's direction and strength, providing further proof that the probe had entered new territory. This was expected, as the sun's magnetic field, carried outward by the solar wind, has a different orientation from the interstellar magnetic field. A final confirmation came from the plasma wave instrument, which detected an increase in the density of the plasma surrounding the spacecraft. Plasma is less dense inside the heliosphere and more dense in interstellar space. When Voyager 1 reported this rise in density, scientists were convinced it had passed through the boundary. Voyager 2 followed, crossing the heliopause in November 2018. Its passage was even more detailed, because its plasma instrument was still functional, allowing it to directly measure the density, temperature, and speed of the plasma. Like its twin, it registered a decrease in solar wind particles and an increase in interstellar ones, corroborating Voyager 1's data. The crossing occurred at a slightly different distance, proving that the boundary is not a fixed line, but a dynamic frontier that shifts and fluctuates. Beyond the heliopause is the true beginning of interstellar space. The interstellar medium, while incredibly thin, fills the galaxy with dust from ancient supernovae. The gas that forms new stars, and twisting electric and magnetic fields. This environment is colder, denser, and more mysterious than the space inside our solar bubble. The heliopause is a frontier that marks the end of the Sun's protection and the start of the vast open galaxy. For the first time, human-made machines have crossed it, touching a part of space not governed by our star. The Voyager probes are now billions of miles away, and their signals take over 16 hours to reach Earth. Though their instruments are old and their power is fading, they continue to drift and send back information from this cosmic shoreline. The common perception of the solar system, with 8 planets orbiting the Sun and emptiness beyond Neptune, is incomplete. In reality, the solar system is far more extensive and complex, stretching well beyond the last known planet. Much of its mass structure and mystery is contained in its outer regions, which cannot be seen with ordinary telescopes. These zones are filled with icy bodies, dust, and faint magnetic forces that form the true boundary of the solar system. Just beyond Neptune, about 30 times Earth's distance from the Sun, is the Kuiper Belt, a ring of icy debris that is much larger and colder than the asteroid belt. It is home to Pluto and other dwarf planets such as Eris Haumea and Makemake. In addition to these larger objects, the Kuiper Belt contains countless smaller bodies, including frozen rocks and remnants from the solar system's early history. Although it may appear empty, scientists believe the Kuiper Belt could contain hundreds of thousands of icy objects over 100 kilometers wide. Some researchers suggest that unseen forces are influencing the orbits of these objects, possibly indicating the presence of an undiscovered distant planet known as Planet 9. This theory remains unconfirmed, but the unusual orbits of certain Kuiper Belt objects sustain the mystery. Farther out still lies the Oort cloud, a theoretical region that cannot be directly observed. Unlike the disc-shaped Kuiper Belt, the Oort cloud is thought to be a vast spherical shell that surrounds the entire solar system. It may begin as close as 2,000 times Earth's distance from the Sun and extend to nearly 100,000 times that distance, a span so large it takes light almost 2 years to cross. The Oort cloud is considered the source of long-period comets, which are thought to be nudged from their distant orbits by the gravity of passing stars or galactic tides. When these comets travel inward, they offer a brief view of material that has remained largely unchanged since the solar system's birth. No spacecraft has visited the Oort cloud, and no telescope has seen it directly. All knowledge of it is inferred from observing cometary orbits. However, most scientists believe it exists and may contain billions or even trillions of icy bodies ranging from the size of mountains to worlds. The heliosphere, the Sun's magnetic bubble, can be considered the solar system's outer wall, but the system's material extends much farther out to the Oort cloud. Therefore, the solar system's size can be defined by its magnetic influence, its orbiting objects, or its gravitational pull. Most of its volume is composed of dark, cold regions that have never been visited but may hold clues to our past. The Oort cloud, for instance, may contain the same icy materials that formed the outer planets, and studying it could reveal what the early solar system was like. The Kuiper Belt is also a frozen record of the past, as its objects have likely changed very little over billions of years and may contain organic molecules, water ice, and other ancient materials. These distant regions might even hold objects that did not form in our solar system. It is possible that during the solar system's early history, passing stars contributed debris to our Oort cloud, or that our Sun captured icy bodies from nearby systems when it was part of a dense star cluster. If so, The outer solar system may hold a history shared with other stars. While we often focus on the planets, the bulk of the solar system's volume and mystery lies in the deep cold beyond them. No spacecraft are currently exploring these far regions directly. Only the Voyager probes drifting ever farther continue to report from the edge. Future missions may eventually be launched to the Kuiper Belt. Or farther, it is possible that one day a probe will be built to reach the Oort cloud, or even depart the solar system to travel toward another star. For now, however, we must rely on faint signals, cometary paths, and distant calculations. A light year, the distance light travels in 1 year, is roughly 95 trillion kilometers. This number is so vast that it becomes meaningful only through comparison. Light takes just over 1 second to get from the Earth to the Moon, and about 8 minutes from the Sun to us. The nearest star system, Alpha Centauri, is more than 4 light years away, which is a considerable trip even at light speed. However, we cannot travel at the speed of light. According to Albert Einstein's theory of relativity, no object with mass can reach or exceed the speed of light in a vacuum, a constant known as c. As an object with mass accelerates, it requires increasing amounts of energy. Near the speed of light, the energy needed becomes infinite, which is unattainable. As a result, we travel at what are by cosmic standards crawling speeds. Voyager 1, for example, moves at about 17 km/s or 61,000 km/h. While this seems fast compared to a passenger jet speed of 900 km/h, it is incredibly slow in a cosmic context. At its current speed, Voyager 1 would need over 70,000 years to reach Proxima Centauri. The nearest star Voyager's velocity was not a primary design goal. It was achieved through gravitational assists from Jupiter and Saturn. Since then, we have built faster probes. The Parker Solar Probe, for instance, has achieved speeds over 190 km/s, about 690,000 km/h, as it orbits the Sun, making it the fastest human-made object. Even at that speed, reaching the nearest star would take more than 6,000 years. If we could reach just 1% of the speed of light, approximately 3,000 km/s, the journey to Proxima Centauri would still last over 400 years, and we currently lack the technology to accelerate to such a speed. The difficulty is rooted in energy. The faster an object travels, the more energy it requires. This challenge extends beyond the amount of fuel to how that fuel is carried, how it is used, and the engine's capabilities. Modern rockets are extremely inefficient for high-speed travel because they must carry their own propellant. Adding more fuel increases the rocket's mass, which then requires even more fuel to propel it. This cycle adds significant weight without a corresponding increase in speed, which is why spacecraft expend most of their fuel just to leave Earth. Once in space, they coast with little to no power, a method sufficient for missions to nearby planets, but inadequate for traveling trillions of kilometers. Another significant obstacle is the human lifespan. Journeys that take centuries are not feasible for humans. At even a small fraction of light speed, reaching another star requires an immense amount of time. A ship traveling at 0.01% of the speed of light would take more than 40,000 years to arrive at Alpha Centauri, a period longer than all of written history. Theoretically, higher speeds are possible with engines that do not rely on traditional fuel. Some scientists and engineers envision spacecraft propelled by giant lasers or solar sails. While these concepts are in early stages, they suggest it may one day be possible to reach 10% or even 20% of light speed. At 10% of light speed, a trip to Alpha Centauri would take about 40 years, which is within a single human lifetime. However, traveling at a significant fraction of the speed of light presents new problems. Space is not empty. It contains tiny particles of dust and atoms. At relativistic speeds, these particles become projectiles. A grain of sand striking a fast-moving spacecraft could have the impact of a bomb, and designing shielding for this is a major engineering challenge. Time itself also behaves differently. At high speeds, as described by Einstein's theory, for a person on a fast-moving ship, time slows down relative to people on Earth. At near light speed, a year on the ship might correspond to 10 years passing on Earth. This effect is real and has been proven with atomic clocks on jets and satellites, but at our current low speeds, it is negligible. At relativistic speeds, this time, dilation would mean a trip to another star might take only a few years for the travelers, while decades passed at home, raising complex questions about such exploration. The speed of light remains a cosmic rule that shapes all our activities in space. It delays our communications, slows our probes, and confines our dreams of visiting other stars to very long timescales. Yet this speed limit also defines our view of the universe, as the light from distant galaxies has taken billions of years to reach us. For now, the most practical approach is to slowly push our limits with smarter engines, lighter spacecraft, and better energy systems. We may not break the speed of light, but we can gradually close the gap over centuries. Someday a probe may leave Earth and reach another star. It may be unmanned and on a one-way trip, but it will represent humanity's slow movement into the deeper galaxy. Until then, by cosmic standards, we are almost stationary. The Voyager 1 and Voyager 2 missions were launched during a rare planetary alignment that occurs only once every 176 years. This specific arrangement of planets allowed the spacecraft to use gravity as a slingshot, gaining speed at each planetary pass with very little fuel. NASA took advantage of this opportunity to launch what would become the longest operating space missions in history. Voyager 2 launched first on August 20th, 1977, and Voyager 1 followed on September 5th. Despite its later launch, Voyager 1 used a faster route and overtook its twin within months. Each spacecraft carried instruments to study planets and their environments, as well as a golden record containing sounds and images from Earth, a message for any civilization that might one day find them. In their early years, the probes conducted unparalleled missions. Voyager 1 flew by Jupiter in 1979 and Saturn in 1980, sending back unprecedented photos of Jupiter's storms and volcanic eruptions on its moon, Io. At Saturn, it revealed new details about the rings and passed close to the moon. Titan, an encounter that set it on a new trajectory out of the solar system's main plane. Voyager 2 took a different path, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It is still the only spacecraft to have visited the latter two planets, discovering new moons and mapping their magnetic fields. Its pass of Neptune was particularly close, coming within 5,000 kilometers of the cloud tops. These planetary flybys increased the probe's speeds. Jupiter's gravity accelerated Voyager 1 toward Saturn, and Saturn's gravity then launched it toward interstellar space. Voyager 2 used a similar multi-step process. In each instance, a giant planet's gravity bent the probe's path and added energy to its flight, achieving a velocity that would have been impossible with its limited onboard fuel. Gravity enabled the long journey of the Voyager probes. After visiting the planets, both spacecraft continued onward, transitioning from planetary missions to interstellar scouts. Despite being decades old, both probes continue to communicate with Earth. Their signals are faint, yet they still transmit data. The cameras were deactivated long ago to conserve power, but the remaining instruments provide a sense of the conditions at the edge of the sun's influence. The probes are still drifting outward with no specific destination, heading into empty space. In approximately 300 years, they will arrive at the inner edge of the Oort cloud, which they may exit entirely in 30,000 years. Afterward, they will continue through the galaxy. These small machines, constructed with 1970s technology and still functioning billions of kilometers away, are incredible accomplishments. However, they also reveal how little progress has been made in genuine interstellar travel. In almost 50 years, nothing has been built that can overtake them, and no other spacecraft has traveled as far. Their technology is obsolete, and their computers are primitive by modern standards, with each possessing only about 68 kilobytes of memory, less than a single digital photograph. Nevertheless, they remain the most distant human-made objects. While we have learned a great deal from them, they also underscore the disparity between ambition and reality. Interstellar flight requires power, precision, time, and technologies that are only now being conceptualized. The Voyagers did not overcome these challenges. Instead, they circumvented them by being small, unmanned, and slow. They demonstrated what could be accomplished with patience and strategic planning, but not how to send humans or fast probes beyond the solar system. Currently, both probes are gradually losing power as their radioisotope generators decay, producing less heat and electricity annually. To prolong their operational life, engineers have been shutting down instruments sequentially. Sometime in the 2030s, both Voyagers are expected to cease transmitting. They will become silent and dark, continuing to drift intact, but no longer sending information to Earth. They will, however, continue their flight long after Earth changes, and their signals are no longer detectable, tracing solitary paths among the stars as our messengers and imprints on the void. To leave Earth and travel into deep space, rather than merely hovering in orbit or flying past the moon, requires a significant expenditure of energy. Entering space demands force, speed, and planning, but it fundamentally requires delta V. Delta V, meaning a change in velocity, is a measure in spaceflight of a spacecraft's capacity for maneuvering. It functions as a fuel budget. Each time a spacecraft uses its engines to accelerate, decelerate, or change course, it consumes a portion of this budget. A larger delta V allows for more maneuvers, while a smaller one imposes greater limitations. The challenge is that space is vast and dominated by gravity. Escaping Earth's gravity well is one of the most energy-intensive phases of any mission. Reaching low Earth orbit at an altitude of just 300 kilometers requires approximately 3 to 10 kilonewtons of delta V, which consumes most of a typical rocket's capacity. Consequently, by the time a spacecraft is in orbit, it has used the majority of its energy simply leaving the ground. Subsequently departing from Earth's orbit toward destinations like Mars or Jupiter necessitates even more delta V. This is not for climbing directly out of Earth's gravitational field, but for increasing speed relative to the Sun. Earth orbits the Sun at nearly 30 km/s, and to escape the Sun's gravity entirely, a spacecraft must exceed 42 km/s. Achieving this speed requires more fuel, which adds weight, in turn requiring more fuel to lift. For this reason, interplanetary missions are planned around specific launch windows and gravity assists. A probe cannot be launched toward any destination at any time. Instead, mission planners wait for precise planetary alignments to use the most efficient trajectory known as a transfer orbit, which may only be available once every few years. Even with optimal timing, the spacecraft must be extremely light and efficient. To conserve fuel, missions often utilize the gravitational pull of planets. A spacecraft flies near a planet, and the planet's gravity accelerates it in a new direction. This maneuver is fuel-free, but demands exact timing and distance. Each planetary assist is meticulously planned, as a minor error in angle or timing could require a substantial amount of delta V to correct. In deep space, course corrections are costly and become more so with distance from the starting point. A 1-degree heading error early in a mission could later require tens or hundreds of kilograms of fuel to fix. This is why trajectory planning is a critical aspect of mission design, and why rockets consist mostly of fuel. A typical rocket's payload is only about 5% of its total mass. The remainder is fuel and its tanks. The Saturn V rocket, which took astronauts to the moon, was 110 meters tall, but the command module it carried was only the size of a small truck. The rest of the rocket was fuel, consumed in minutes to lift that small component out of Earth's gravity. This problem intensifies with greater distances into space. While a spacecraft to Mars can coast for much of its journey, once on course, a mission into interstellar space requires far more energy and delta V. Planetary assists are not indefinitely available. Beyond Neptune, there are no large bodies to provide a gravitational boost. At this point, the constraints of delta V become severe. Simply adding more fuel is not a viable solution, as the returns diminish rapidly. This is described by the rocket equation, a constant challenge in which every velocity gain has an exponential, not linear cost. Doubling a spacecraft's speed might require 4 times the fuel or more. The mathematics are unforgiving, which is why many space missions are slow. Engineers would prefer faster travel, but the cost of speed is prohibitive. Voyager 1 took 35 years to reach the heliopause, and New Horizons required 9 years to reach Pluto, even with a gravity assist from Jupiter. The Parker Solar Probe, our fastest spacecraft, achieves its speed by falling toward the Sun, not by escaping it. To leave the solar system in a reasonable time frame, a future spacecraft would need to travel much faster than current technology allows, which would demand an impossible amount of fuel if using conventional rockets. Consequently, engineers are exploring alternative propulsion methods, like solar sails, nuclear propulsion, and fusion drives. These concepts may eventually overcome the limitations of delta V, but they are not yet a reality. In some respects, landing on other worlds is less difficult than leaving them. An atmosphere, such as on Mars or Earth, can be used for deceleration with heat shields and parachutes. However, departure requires engines and fuel to counteract gravity once more. This is why the Apollo astronauts left the lower stage of the lunar lander on the Moon. The ascent stage launched back into orbit with just enough fuel for the return journey, with every gram of mass accounted for. This principle applies to future missions. A mission to Mars might depend on producing fuel on site by extracting oxygen from the atmosphere, or by separating water into hydrogen and oxygen, as transporting all necessary fuel from Earth would be too heavy and expensive. Delta V is the metric that defines the limits of what is possible in space exploration. It determines our destinations, the duration of our stay, and the cargo we can carry, shaping the entire framework of space missions. Until a method is found to circumvent its constraints, it will continue to govern our aspirations of traveling beyond Earth and the solar system. In December 1972, the Apollo 17 mission returned from the Moon, and no human has traveled farther since the mission commanded by Eugene Cernan. concluded a rapid and ambitious era of lunar exploration and represents the only time humans have ventured beyond low Earth orbit. For over 50 years, all subsequent astronauts have remained within a few hundred kilometers of the planet. Despite more advanced computers probes being sent to the solar system's edge and private companies launching rockets into orbit frequently, each month, humans have not traveled beyond low Earth orbit in half a century. The explanation involves a combination of cost-risk and evolving objectives. Sending humans far from Earth is an endeavor of immense difficulty. Although the Apollo program was a monumental achievement, it did not establish a sustainable framework for long-term spaceflight. It was a singular event, rather than a permanent bridge to deep space. Following the moon landings, the United States shifted its national priorities. By the early 1970s, factors such as the Vietnam War, domestic economic pressures, and a changing political climate made it difficult to sustain funding for missions that no longer seemed urgent. NASA had accomplished its primary objective of landing on the moon before the Soviets, and with this national challenge met a clear justification for continuing such missions. Diminished. Plans for Mars, missions or permanent lunar bases were consequently shelved. The subsequent major initiative was the Space Shuttle. Designed as a reusable vehicle, it was intended to replace the single-use rockets of the past. The concept was for a craft that could launch vertically and land like an airplane, with the goal of making space travel more affordable, safe, and routine. In practice, the shuttle proved to be a complex and costly system. While it never achieved the anticipated cost reductions, the program defined NASA's focus for several decades. The shuttle's primary role was the construction and maintenance of space stations in low Earth orbit, such as Mir and later the International Space Station. These missions yielded crucial data on the human body's response to long-term space travel, including bone density, loss, muscle atrophy, and fluid shifts in microgravity. However, they also confined human spaceflight to areas near Earth, as the shuttle was limited to orbits of approximately 300 to 600 kilometers in altitude. As a result, deep space exploration was relegated to robotic missions. The challenges of sending humans farther persisted. Deep space entails not just greater distances, but also fundamentally different types of hazards. Beyond Earth's protective magnetic field, radiation becomes a critical concern. Astronauts are exposed to high-energy particles from solar and cosmic sources, which can damage cells and increase the risk of cancer or neurological problems. Designing effective yet lightweight shielding against this radiation is a significant engineering challenge. Furthermore, life support for long-duration missions lasting weeks to years requires highly reliable systems for air recycling, water recovery, food storage, and waste management. A single system failure could be catastrophic, and unlike the International Space Station, such missions cannot depend on regular resupply from Earth, demanding complete self-sufficiency. While a return from low Earth orbit can be accomplished in hours, rescue is not a possibility in deep space. A mission to Mars, for instance, would require months of travel, one way, and a critical system failure. Mid-journey would preclude any possibility of turning back. The spacecraft must therefore be entirely self-sufficient, with a crew capable of resolving any issue independently. Achieving this level of redundancy and safety is exceptionally expensive. The launch vehicle itself is another major factor. The Saturn V rocket, which powered the Apollo missions, remains the most powerful rocket ever successfully launched. It was, however, an expendable system, and recreating a similar capability would require years of development and an investment of tens of billions of dollars. In the decades following Apollo, there was no political or public will to commit such funds. Instead, space agencies prioritized robotic missions. Probes such as Voyager Galileo, Cassini, and Curiosity explored the solar system without the need for life support and with no risk to human life. Robotic exploration has been a critical preliminary step, allowing us to gather essential data such as the composition of Martian soil and the location of lunar water ice before sending humans. Even with this knowledge, developing the technology to sustain human life for extended periods in space without resupply remains an ongoing challenge. The situation is now evolving. NASA has developed the Space Launch System. Private companies like SpaceX are creating their own heavy-lift vehicles, and programs such as Artemis are planning for a return to the Moon. However, these efforts represent only the initial steps in resuming human deep space exploration, as they still confront the formidable limitations of radiation, life support, distance, and time. The long hiatus from human exploration beyond low Earth orbit is not due to a lack of vision. Rather, it is because every mission beyond Earth's protective environment is a high-risk venture into the unknown. Until systems can be developed to manage these risks reliably, repeatedly, and affordably, human travel will remain limited to near-Earth space. The performance limitations of rockets are rooted in their fundamental design, centered around the combustion chamber, where fuel and an oxidizer combine and combust under extreme pressure. The resulting hot high-velocity gases are expelled through a nozzle to produce thrust. This process is subject to physical constraints, as the chamber materials must withstand immense heat and stress. Exceeding these limits leads to structural failure. Although decades of engineering have led to stronger alloys and improved cooling systems, the majority of contemporary chemical rockets still operate with chamber pressures between 100 and 300 atmospheres. Simply increasing pressure to gain more thrust is not always effective, as it can cause overheating, structural integrity issues, or inefficient combustion. The nozzle also presents design challenges. A nozzle optimized for sea-level atmospheric pressure operates inefficiently in a vacuum, and vice versa, which is why multi-stage rockets are used, with each stage optimized for a specific altitude range. Despite these optimizations, a more fundamental limitation exists. A rocket's achievable velocity is determined not only by its fuel quantity, but also by its exhaust velocity. Even the most advanced chemical rockets have a maximum exhaust velocity of approximately 4 to 5 kilometers per second. Consequently, propellant often constitutes more than 90% of a rocket's total launch mass. Modern launch systems, including Falcon Heavy and Artemis, operate on the same principle of chemical combustion and are therefore subject to a similar performance plateau, as there is a finite amount of energy that can be extracted from chemical bonds. Specific impulse, a key metric of engine efficiency, reaches a maximum of about 450 seconds for the most effective liquid fuel engines. Achieving higher velocities requires alternative propulsion methods. Engineers are exploring options such as electric propulsion, ion drives, and nuclear-powered systems. These technologies utilize electric fields or nuclear reactions to eject particles at significantly higher velocities. Ion engines, for instance, can achieve exhaust velocities up to 10 times greater than those of chemical rockets, making them vastly more efficient. The drawback, however, is that these systems produce extremely low thrust. They are incapable of lifting a vehicle from Earth's surface and require weeks or months in space to gradually increase a spacecraft's velocity. This presents a persistent trade-off. High-thrust systems are generally inefficient, while high-efficiency systems produce low thrust. Currently, no single-engine technology provides both. As a result, deep space missions are structured as a compromise, involving a powerful chemical launch, followed by a long coasting phase with low thrust engines leading to very long transit times. This is why, despite significant technological progress, interstellar travel remains a distant goal, as current rocket technology is constrained by fundamental physical limits. The velocity of fuel expulsion cannot be increased, the mass of fuel tanks cannot be reduced, and the energy density of fuel cannot be raised without risking structural failure. Consequently, current spacecraft travel slowly, particularly in the outer solar system, constrained by the limitations of fuel mass and the principles of rocket physics. Rockets operate differently from conventional vehicles. They must carry their entire fuel supply from launch and cannot be refueled. A rocket functions not by pushing against an external surface, but by expelling mass, burned fuel, backward through a nozzle. This action produces forward thrust with the rocket effectively pushing against its own exhaust. To increase a rocket's speed, range, or payload, one cannot simply add more fuel due to a fundamental principle known as the rocket equation. This equation states that a rocket's potential change in velocity, delta V, is determined by its exhaust velocity and the proportion of its total mass, that is fuel. Consider a rocket with a dry mass, structure, and payload of 1 ton. Adding 1 ton of fuel creates a total mass of 2 tons. When this fuel is expelled, the rocket achieves a specific delta V. To achieve a higher velocity, one might add another ton of fuel, increasing the total mass to 3 tons. This additional fuel, however, must propel not only the payload, but also the initial ton of fuel. Making this second ton of fuel effective requires even more fuel to propel it, leading to a compounding increase in mass. To double a rocket's delta V, it may be necessary to use 5 or even 10 times the original amount of fuel. This leads to a point where the vehicle is composed almost entirely of fuel and engines, with the payload being a minimal fraction of the total mass. Adding more fuel provides diminishing returns, a problem known as the exponential trap. This limitation is an inherent principle of physics, not a flaw in engineering. The rocket equation shows that for each linear increase in velocity, the required initial mass of the rocket grows exponentially. This is why rockets are often large and consist mostly of propellant. One method to mitigate this is staging. The Saturn V rocket, for example, jettisoned empty fuel tanks as it ascended. Each stage was discarded after use, allowing the remaining vehicle to accelerate more efficiently by shedding mass. Even with staging, the challenge is significant. The first stage lifted the second lifted the third, and only the final stage carried the Apollo capsule to space. The rocket equation applies universally to launch a 500-kilo probe to a delta V of 9 kilometers for a deep space trajectory using a standard chemical engine with an exhaust velocity of 4.5 kilometers. The required fuel mass would be approximately 8 times the dry mass. This means 4,000 kilos of fuel would be needed to push the 500-kilo probe. To increase the velocity to 12 kilometers per second, the requirement grows to nearly 20 times the dry mass, or 10,000 kilos of fuel. To reach 15 kilometers per second, the fuel requirement becomes over 50 times the dry mass, or 25 tons of fuel for a small increase in speed. This illustrates how quickly fuel requirements can escalate from feasible to impractical. The majority of this fuel is used to propel other fuel, not the payload itself. Strategies exist to work within these constraints, such as assembling spacecraft in orbit to avoid launching the entire mass from Earth, or using alternative propulsion systems with higher efficiency. However, these methods offer only incremental improvements, as the fundamental principles of the rocket equation still apply. The space environment, though appearing empty, contains significant invisible hazards, including pervasive radiation from the sun, distant stars, and ancient cosmic events. This radiation consists of high-energy particles traveling near the speed of light that are harmful to the human body. Earth's magnetic field acts as a protective barrier, trapping charged particles in two regions, known as the Van Allen belts. Discovered in the late 1950s, these belts of protons, inner, and electrons, outer, are the first radiation obstacle for spacecraft leaving Earth. While a rapid transit is not lethal, prolonged exposure results in a significant accumulation of radiation. The Apollo missions navigated this hazard by plotting a quick trajectory under an hour through the thinnest parts of the belts to minimize exposure. Beyond Earth's magnetosphere, astronauts are exposed to deep space radiation, primarily solar particles and galactic cosmic rays. During solar flares or coronal mass ejections, the sun can eject massive quantities of particles, causing radiation levels to spike for hours or days. These solar storms are difficult to predict and can pose a serious or fatal threat to unprotected astronauts. While the International Space Station crew remains within the magnetosphere and has access to shielded areas, a long-duration mission to Mars offers no quick retreat. Mission plans may include a small, heavily shielded storm shelter made of plastic or water tanks, but this adds mass galactic cosmic rays are a more severe threat. Originating from events like supernovas, these high-energy particles can penetrate most spacecraft hulls, damage human DNA, and increase cancer risk. Effective shielding would require meters-thick layers of dense material like lead or water, which is prohibitively heavy for most missions. Space radiation exposure is measured in units of biological harm, such as sieverts. On Earth, a person receives about 2 to 3 millisieverts per year from natural sources. A 6-month trip to Mars could expose an astronaut to 300 millisieverts, or more, increasing the risk of cancer, immune system damage, neurological damage, and accelerated aging. Robotic probes are not susceptible to these biological effects. Their electronics can be hardened, and if they fail, they can be replaced. Humans, however, are biologically vulnerable and irreplaceable. Designing a human-rated spacecraft involves trade-offs. More shielding increases safety but adds mass, which requires more fuel, larger rockets, and higher costs. Material choice is also critical. Metals like aluminum can generate secondary radiation, while plastics and water can be more effective. Some designs propose using onboard water or food supplies as supplemental shielding. Space agencies test materials and model spacecraft designs to assess protective capabilities, but simulations have limitations. No human has undertaken a year-long mission beyond Earth's magnetic field, so the long-term health effects are unknown. The longest continuous human spaceflight was just over a year aboard the International Space Station, within the magnetosphere's protection. A round-trip mission to Mars would last 2 to 3 years, involving far greater exposure, and would culminate on a planet with a thin atmosphere and no protective magnetic field. Cosmic rays remain a threat to space travelers. One proposed solution is to schedule missions during the solar maximum, the period of greatest solar activity. Although counterintuitive, the heightened solar wind during this time deflects some galactic cosmic rays. This creates a trade-off: increased solar radiation in exchange for reduced radiation from beyond the solar system. Another suggestion involves constructing underground habitats using Martian soil for shielding, but this solution is only viable for a planetary base and not for transit. The human body's vulnerability is a fundamental constraint on space travel, as machines can endure greater speeds, distances, and more severe environments. To enable human exploration, the radiation issue must be addressed through improved materials, advanced ship designs, or new propulsion systems that reduce travel time and thus exposure. Currently, each additional day in space increases exposure to this harmful radiation. Project Orion was a concept developed in the late 1950s and early 1960s by engineers seeking a method for interstellar travel. The project was based on the premise that if chemical rockets lacked the power for such journeys, a more powerful source, nuclear bombs, should be used. The fundamental plan was to construct a spacecraft propelled by a series of nuclear explosions. The proposed design featured a robust flat pusher plate at the vessel's rear connected to a system of large mechanical shock absorbers. The propulsion mechanism involved ejecting and detonating small nuclear bombs sequentially behind the spacecraft at a precise distance. The resulting shock wave from each blast would impact the pusher plate, and the shock absorbers would mitigate the force, converting the successive impacts into forward momentum. The project involved respected scientists and engineers, initiated in 1958 under the direction of individuals such as physicist Freeman Dyson and engineer Ted Taylor. Their goal was to surpass the inherent limitations of chemical propulsion in spaceflight. The performance calculations were remarkable. A well-designed Orion spacecraft, propelled by numerous small nuclear detonations, could achieve speeds unattainable by chemical rockets. Projections estimated speeds between 3% and 10% of the speed of light, which would make interstellar travel a possibility, reducing journeys to other star systems from centuries to decades. A key performance metric was specific impulse, which measures the thrust generated per unit of fuel, whereas chemical rockets have a specific impulse in the hundreds of seconds, and nuclear thermal rockets in the low thousands. Orion projected specific impulses in the tens of thousands of seconds, a significant improvement. The system also scaled effectively. A larger Orion vessel could accommodate more bombs for greater thrust and carry more mass, including shielding crew and supplies, thereby performing better at a larger size. Blueprints existed for very large Orion designs, such as the 4,000-ton Super Orion, which would have been powered by hydrogen bombs and capable of reaching Saturn in months or nearby stars in decades. Freeman Dyson noted that any craft built to reach Alpha Centauri within a human lifetime would likely resemble an Orion ship. Small-scale experiments, rather than full nuclear tests, were conducted. Engineers utilized chemical explosives to assess the effect of a shock wave on a pusher plate and to model the plate's durability and the transmission of shocks throughout the structure. They also developed solutions for the timing of detonations, estimated at 1 every 1 to 2 seconds, and for the precise ejection of the bombs. The challenges were significant, but considered surmountable. The project encountered a major obstacle as global awareness of the dangers of nuclear testing grew in the early 1960s. Concerns about radioactive fallout from atmospheric explosions, its spread, and its long-term health effects became widespread. The 1963 Partial Test Ban Treaty, signed by the United States, the Soviet Union, and the United Kingdom, prohibited nuclear explosions in the atmosphere, underwater, and in outer space. This treaty effectively outlawed Orion's propulsion system. Since violating the treaty was not a viable option, the project could not be tested. Although it initially had military support, this waned due to the risks associated with detonating nuclear devices in space near Earth or satellites. Consequently, funding was withdrawn. The engineers pursued other work, and Project Orion was discontinued. However, the concept of nuclear pulse propulsion has not been completely abandoned and continues to be a subject of theoretical research. While physically possible, it conflicts with political realities, safety concerns, and public perception. Even without treaty restrictions, significant technical hurdles would remain. Each detonation would produce high-energy particles capable of damaging the spacecraft or its electronics. The shock wave could be difficult to manage, and the sequence of explosions would demand exceptional precision. Furthermore, the use of numerous small nuclear devices would create challenges related to their storage arming and the risk of accidental detonation. Despite these issues, Project Orion demonstrated a theoretical pathway for interstellar travel within a human lifetime, offering a powerful alternative to slow chemical or electric propulsion systems. Modern variations have been proposed, such as using fusion devices instead of fission, or constructing and launching the spacecraft far from Earth. Another concept, known as Medusa, suggests using a large sail to capture the blast wave instead of a solid plate to reduce structural stress. These ideas remain conceptual, with no active development by any nation. The legacy of Orion highlights the disparity between the goals of space exploration and current technological capabilities. Although political factors terminated the project, it represents the only propulsion system conceived to date that could potentially transport humans to another star using existing knowledge and materials. In the 1970s, a group of engineers and scientists from the British Interplanetary Society, an organization with a long history in spaceflight theory, initiated Project Daedalus. Lacking significant resources such as labs or government funding, they undertook a conceptual study for interstellar travel. The project's objective was to design an unmanned probe capable of reaching Barnard's star, a red dwarf approximately 6 light-years away. At the time, this was the second closest known star system, and it was thought to potentially host a planet. The design was not based on 1970s technology, but on systems considered achievable in the near future, with the goal of determining the feasibility of interstellar travel. The resulting study is one of the most detailed conceptual plans for an interstellar spacecraft. The proposed Daedalus vessel was massive, with a length exceeding 190 meters and a launch weight of 54,000 tons, predominantly fuel. Its propulsion system was based on nuclear fusion, distinct from chemical rockets or the nuclear fission of Project Orion. The mechanism involved using powerful electron beams to compress pellets of deuterium and helium-3, inducing microfusion explosions. The energy from these explosions would then be channeled by a magnetic nozzle to generate thrust. In contrast to Project Orion, Daedalus utilized a more refined but also more delicate system that did not rely on conventional bombs. The control of nuclear fusion presents significant challenges demanding precise timing, immense energy input, and a stable reaction. A key component of its fuel, helium-3, is extremely scarce on Earth, leading the project team to presuppose that it would need to be sourced by mining the atmospheres of gas giants such as Jupiter. Project Daedalus was conceived as a 2-stage spacecraft. The first stage was designed to fire for over 2 years, accelerating the probe to approximately 7% of the speed of light. After depleting its fuel, the first stage would detach, and the second stage would ignite for more than a year, increasing the vessel's speed to a final cruising velocity of about 12% of the speed of light. At this speed, the ship would reach Barnard's star in roughly 50 years. The mission was an uncrewed one-way trip with no planned method for the spacecraft to slow down or stop. Upon launch, it would travel through space for decades, collect images and data as it passed its target system, and then continue into deep space. No recovery was planned. Only a brief transmission of data was expected before contact was permanently lost. Project Daedalus was in many aspects the opposite of Project Orion. Orion was envisioned as a blunt, heavy vehicle intended to transport people, whereas Daedalus was a sleek, fast robotic probe. Orion's design depended on brute force, while Daedalus was intended to use controlled fusion reactions, with each reaction releasing energy in a precisely guided direction. Neither spacecraft was ever constructed. They exist as detailed, thoughtful, and ambitious engineering studies, but remain conceptual. Cost is one reason for this. A Daedalus mission would have been enormous in terms of financial and time investment. It would have required fusion reactors, helium-3, mining the precision, manufacturing of pellet fuel, and deep space communication systems capable of receiving signals from 6 light-years away. Another reason is that functional fusion power has not yet been achieved on Earth, let alone on a spacecraft. Controlled sustained fusion has been a long-standing goal, but it has proven difficult to achieve. Laboratories attempting it face recurring problems with sustaining the reaction, managing the heat, handling the materials, and ensuring efficiency. The challenge of implementing this technology in a terrestrial power plant is even greater for a spacecraft moving at a fraction of light speed. A successful Daedalus mission would have returned a few years of data, at most providing a snapshot of a distant star system from a probe that would be forever inaccessible. In an environment of tight budgets and demand for quick results, it is difficult to persuade a government or private company to fund a project that may not yield a return for 50 years. However, Daedalus established a benchmark. Years later, the same group proposed a new design, Project Icarus, which was a modernized version of Daedalus utilizing newer materials and updated models. Other groups have also pursued similar concepts. Initiatives like Breakthrough Starshot propose sending small, laser-driven probes to Alpha Centauri at a significant percentage of light speed, using different technologies and for different purposes. Daedalus, however, continues to be one of the most well-defined concepts for practical interstellar flight. It was a vision of a ship built in space, powered by fusion and traveling at immense speed across the interstellar void, not for colonization, but for exploration and knowledge. Nuclear thermal propulsion has been studied since the early period of the space race. The basic concept is straightforward. A nuclear reactor heats liquid hydrogen to thousands of degrees, and the resulting superheated gas is expelled from a rocket nozzle to generate thrust through rapid expansion. Unlike chemical rockets, which generate energy through chemical reactions, nuclear thermal engines utilize nuclear fission to create intense heat that is transferred directly to the propellant. This process yields a much higher specific impulse. With nuclear thermal propulsion, or NTP, a spacecraft could achieve nearly double the performance of a conventional chemical rocket. This translates to higher speeds, larger payloads, or more fuel remaining upon arrival for missions beyond Earth's orbit, such as to Mars or the outer solar system. This enhanced efficiency would be a significant advantage. It would allow for shorter trip times while still delivering adequate supplies for a mission. Unlike chemical rockets, NTP does not require heavy oxidizers. Furthermore, unlike speculative concepts such as fusion propulsion or antimatter drives, nuclear thermal engines have already been built and tested. In the 1960s and 1970s, programs like NASA's NERVA, Nuclear Engine for Rocket Vehicle Application, conducted ground tests of full-scale NTP engines in Nevada. The engines performed successfully, operating at high temperatures with clean exhaust and meeting or exceeding their design specifications. Engineers gained experience in managing the heat, building the reactors, and protecting the systems. Theoretically, the technology was ready for deep space travel. However, the tests were discontinued as political priorities shifted and funding was withdrawn. Decades later, nuclear thermal propulsion development remains stalled. Anything involving nuclear technology faces significant public apprehension. The prospect of launching a rocket from Earth with an active nuclear reactor on board raises profound fears. The possibility of an accident, however remote, is a major public concern. A single launch failure could disperse radioactive material over a large area. Regardless of the number of safety systems in place, the perceived risk is more personal than with other technologies. Although chemical rockets have exploded on launch pads and satellites already use radioactive power sources, the idea of activating a nuclear reactor in the atmosphere is still seen as crossing a critical threshold. Another obstacle arises from international treaties. The Outer Space Treaty of 1967, along with other agreements, places limits on the types of nuclear materials that can be used in space. While these laws do not outright prohibit nuclear propulsion, they mandate extensive reviews, strict controls, and international cooperation. As space becomes increasingly crowded and contested, these legal hurdles are becoming more significant. Nations are suspicious of one another's intentions. A nuclear-powered spacecraft could be interpreted as a weapon, and this ambiguity causes widespread nervousness. Cost is also a considerable issue. Manufacturing a nuclear rocket engine is an expensive endeavor that requires highly enriched uranium radiation, shielding, and specialized production, all under strict oversight. Test facilities must be remote secure and equipped to manage potential risks. Few locations in the world have these capabilities, and fewer still have the political will to fund such work. When compared to the relative simplicity of chemical propulsion or solar electric drives, NTP represents a high barrier to entry. Nevertheless, the benefits are apparent. A nuclear thermal engine does not rely on exotic fuels or scientific breakthroughs. It functions using heat and hydrogen. The designs are robust, providing steady and high thrust, capable of carrying substantial payloads. For a Mars mission, NTP could shorten the round-trip time by several months, offering a major advantage for human spaceflight. NASA has not abandoned the concept. The agency recently restarted NTP research under its Space Nuclear Propulsion Program, collaborating with the Department of Energy. This work involves new materials, new fuels, and advanced safety systems. Some designs propose using low-enriched uranium to minimize proliferation risks, while others feature modern reactors with improved control and higher burn-up rates. Engineers are applying decades of advancements from terrestrial nuclear power to create lighter, safer, and more effective engines for space. Private companies are also becoming involved. Some startups and contractors are investigating compact nuclear designs for deep space missions, seeing a potential market for cargo tugs, interplanetary transport, and nuclear-powered shuttles to support lunar bases. Yet even in the private sector, progress is slow. The regulatory burden is substantial. Testing opportunities are limited, and every advancement must be justified to politicians, the public, and the international community. The situation is that a technology exists that could significantly advance spaceflight capability, but we are not using it because the real and perceived risks have not been adequately managed. The primary constraints are not scientific, but are related to a lack of trust in the technology, in international partners, and in our ability to handle such a powerful system safely. If nuclear thermal propulsion were to be implemented, it could enable human exploration of the solar system, turning aspirational goals into practical realities until the issues of public fear. legal frameworks and costs are resolved. However, it remains an unrealized, powerful idea. The concept of human hibernation suggests that if interstellar distances cannot be crossed within a reasonable number of years, astronauts could instead be put into a state of long-term controlled inactivity. In this condition, the body's metabolism and needs would slow down, allowing time to pass. Hibernation is a well-understood phenomenon in the animal kingdom, observed in bears, squirrels, and even certain birds and reptiles that enter a deep sleep during harsh conditions. In this state, their body temperature and breathing rate decrease, and they subsist on stored fat. Heart rates can fall to a few beats per minute, and for some small mammals, core body temperature drops to just above freezing. These animals can survive for weeks or months before resuming normal life. Humans do not have a natural ability to hibernate, but researchers are studying ways to mimic it, often using animal studies as a guide. One area of focus is torpor, a biological term for a temporary state of reduced activity and metabolism, which is like a short-term form of hibernation. Some animals enter torpor nightly, while others do so seasonally. Scientists believe that safely inducing a torpor-like state in humans could significantly reduce the physical demands of long space missions. Some progress has been made in laboratory settings, and doctors already employ techniques that share similarities with this process. Therapeutic hypothermia, for example, is used during surgeries or after cardiac arrest. Cooling the body slows brain activity and reduces the risk of damage from low oxygen levels. Patients can be kept in a low-temperature state for hours or a couple of days, during which their bodily functions and energy use decrease. This, however, is a carefully managed emergency procedure, not true hibernation, which would need to last for months or even years. No one has yet successfully placed a healthy human into long-duration torpor. The risks are considerable. Unused muscles and bones weaken quickly. Blood flow becomes difficult to manage, and internal organs require constant regulation. Even simple tasks, like regularly repositioning a person to prevent pressure sores, present a challenge. A person in this state still requires food, water, oxygen, and waste removal, though these needs are reduced. One research path involves pharmacology. Scientists are investigating whether certain drugs that mimic the effects of torpor in animals could work in humans. Some studies have shown that hydrogen sulfide, a gas that can lower oxygen consumption, has promise for inducing a low metabolism state in mice. Other compounds are being tested that affect neurotransmitters related to sleep and metabolism. So far, however, no drug or combination of drugs has been able to induce a stable, long-term state of torpor in people. The results are preliminary, small-scale, and uncertain. Another idea is the use of specialized chambers where temperature, oxygen, and pressure can be controlled to guide the body into and out of a suspended state. These systems would be similar to advanced medical beds, equipped with monitors, feeding tubes, and robotic systems for care. The objective would be to keep astronauts alive with minimal activity during long journeys. They would not be unconscious in the traditional sense, but rather in a state of deep suppression where every bodily function is slowed. Their brains would remain intact but inactive. Their hearts would beat more slowly, and their bodies would use less fuel, produce less waste, and require less space. This is a delicate balance. If the state is too deep, there is a risk of organ failure. If it is not deep enough, the benefits are lost. Managing body temperature, especially in space, adds further complications. Safely cooling the human body requires ensuring the core temperature drops evenly to avoid shock, not just lowering the external temperature. In hibernating animals, this process is guided by their natural biology, but in humans, it would need to be controlled moment by moment, using technology to monitor every change, even if the biological challenges are overcome. Practical issues remain. Weightlessness leads to muscle atrophy and bone thinning. And since astronauts in torpor would not be exercising, this problem would be worse. Fluid shifts in the body, which already increase the risk of blood clots and eye problems in space, could become dangerously concentrated during torpor countermeasures, like compression suits or artificial gravity, would need to function effectively during this state. Waking from hibernation is also a complex process. In animals, it is a gradual warming over several hours, accompanied by shivering and slow movements. For humans, re-warming a cold body without causing harm is difficult and would necessitate heating systems, nutrient delivery, and constant medical monitoring should something go wrong mid-voyage, where the systems fail to revive a crew member or the entire crew. The mission would be lost. Therefore, even if hibernation is achieved, fail-safes and redundancy will be crucial. This concept is different from cryogenic freezing, which is the idea of freezing a human completely. When water freezes, it forms ice crystals that destroy cells. While some labs use cryoprotectants to prevent this, these chemicals are toxic in large quantities. No mammal has ever been frozen solid and revived. Some frogs and insects can survive being frozen because they have evolved special proteins and behaviors to manage the damage, which humans have not. Torpor is also distinct from an artificial coma or anesthesia. In those states, the brain is quieted, but the body's metabolism continues at a near-normal rate, requiring regular amounts of oxygen, water, and nutrients. The body ages, muscles waste away, and after weeks or months in a coma, extensive rehabilitation is needed. True torpor would be more like pausing all bodily activity. This leaves the concept of torpor as something that is not impossible. The biological basis exists in nature, and some of the necessary technology is already present in modern medicine. What is currently lacking is a reliable long-term method to apply it to humans in space. It is widely agreed that this capability would be a significant advancement for missions to Mars or the outer planets, as it could reduce requirements for food, water, and psychological support. For missions beyond our solar system, it might be the only viable means of travel. At present, however, the technology is not ready. Research continues, and while science fiction imagines crews sleeping through centuries, the human body currently demands simpler things: to eat, breathe, move, and be awake. Using current technology, a trip to Alpha Centauri, our nearest star at over 4 light-years, about 25 trillion miles away, would take tens of thousands of years. This distance is 160,000 times farther than the distance from Earth to the Sun. The problem with chemical rockets is that they provide a large initial thrust, but then quickly run out of fuel. Even a mission to Alpha Centauri, using our best rockets and optimized in every detail, would still be a journey of many millennia. This has led to other ideas, with one of the most promising being solar sailing. A solar sail functions more like a boat than a rocket, using a large, thin, reflective surface to catch photons from the sun. Photons have no mass, but carry momentum, and over time, this pressure provides slow but steady acceleration. A solar sail requires no fuel, as the sun's light provides the propulsion. A sufficiently large and light sail, if pointed correctly, could reach speeds that chemical rockets cannot. Missions like the Japanese Ikaros spacecraft have demonstrated that this principle works. To be useful for interstellar travel, however, it would need to be scaled up dramatically. involving a sail the size of a football field or larger and a payload smaller than a shoebox. The more sail area and the less weight, the faster the craft can travel. There is also the concept of using lasers from Earth to push these sails instead of relying only on sunlight. This is the idea behind Breakthrough Starshot, a private initiative aiming to send tiny spacecraft weighing just grams to Alpha Centauri. The plan is to use powerful ground-based lasers to accelerate a sail to speeds up to 20% of the speed of light, which would make the trip possible in just over 20 years. This is still theoretical, as no such laser array exists. There are also massive technical challenges, such as guiding the laser over millions of miles and ensuring the sail does not tear apart during acceleration. Even if the system works, the payload would be extremely limited to a chip-sized camera and a power supply, making it impossible to send people or a traditional robotic lander. More realistic solar sails built with current materials and pushed only by the sun would not reach those speeds. The best projections suggest they could achieve a few hundred kilometers per second. While much faster than chemical rockets, this is still only a fraction of a percent of the speed of light. This would reduce travel times to Alpha Centauri from 70,000 years to perhaps 5,000 or 10,000 years. While a significant advancement, the travel time still exceeds a human lifespan, necessitating a mission that would last for many generations. With current technology, interstellar voyages are not feasible for individuals. Such a mission would be undertaken with the knowledge that no one alive at its launch would witness its conclusion. The spacecraft must function autonomously for millennia, relying on small nuclear batteries or a yet-to-be-developed power source. Its software must endure malfunctions, radiation, and cosmic dust. Furthermore, its antennas must maintain precise aim toward Earth over vast distances to transmit a signal, and Earth would need to be prepared to receive that signal, potentially centuries later. It is tempting to consider achieving higher speeds by simply building more powerful engines or adding more fuel, but the physics do not support this approach. This limitation is why unconventional concepts like fusion or antimatter propulsion are suggested. Without an entirely new propulsion method, travel will remain slow. If a journey to the closest star requires 10,000 years, the mission must be either robotic or generational. This involves either deploying machines designed to outlast entire civilizations or sending humans who would pass the mission onto successive generations born during the voyage. Although common in fiction, generational starships present immense real-world complexities, such as creating a closed life support system that can function for centuries and managing the political, psychological, educational, and medical needs of a population within a sealed environment. Therefore, the time required to reach Alpha Centauri with current capabilities is longer than the entire history of human civilization. This does not imply that the attempt should not be made, but it is necessary to acknowledge the existing constraints. Beamed propulsion is a frequently discussed concept for interstellar travel. A laser-based system functions antithetically to a rocket. Rockets are heavy and slow because they must carry their own fuel. In contrast, beaming energy from Earth or an orbital platform allows the spacecraft to forego heavy equipment, reducing it to a sail and a payload, potentially as small as a smartphone. The Breakthrough Starshot initiative proposes using a massive phased array laser system, possibly spanning dozens of square kilometers, to direct powerful beams at a small spacecraft equipped with a light sail. However, this seemingly straightforward concept involves significant technical challenges. The most substantial of these challenges is aiming light naturally spreads and does not travel in a perfectly straight line. Indefinitely, even laser beams, which are more coherent than ordinary light, diverge over great distances. This phenomenon, known as diffraction, is a fundamental consequence of the wave-like properties of light. A perfect laser beam will begin to widen as it travels. The degree of this spread is determined by the light's wavelength and the diameter of the focusing mirror or lens. A 10-kilometer wide optic, though massive, could only maintain a tightly focused laser beam for a few million kilometers before it begins to diffuse. When the beam reaches a destination several light years away, it will have expanded from a concentrated energy stream into a broad, diffuse area, potentially thousands or millions of kilometers in diameter, causing most of its energy to miss the sail. Maintaining focus over such a distance would require impractically large optics. Some calculations suggest that a mirror hundreds or thousands of kilometers in diameter would be necessary to keep a beam focused on a sail en route to Alpha Centauri. Such a structure cannot be built with current technology and may be impossible with any known materials. The optic would need to maintain its form with atomic-level precision over a vast area while in orbit or free space and be aimed with exceptional accuracy. Even a minor aiming error at the outset would result in a significant deviation over light-year distances. A slight disturbance or vibration could cause the beam to drift, even with perfect initial focusing. Mid-course correction is not feasible, as the more than 4-year travel time of light to Alpha Centauri makes any feedback loop, based on a return signal, too slow. The initial aim must be perfect. Consequently, some proposals involve using satellite swarms to track the sail and make stage corrections to the beam. This approach, however, increases both cost and complexity, requiring not one large laser but numerous smaller systems operating in unison in space for extended periods. The sail's stability must also be maintained. A slight tilt or wobble could cause it to deviate from its course or disintegrate from the beam's pressure, particularly during acceleration, when a small craft could experience forces equivalent to thousands of times Earth's gravity. Propelling a spacecraft weighing only a few grams to a substantial fraction of the speed of light requires an immense amount of power, from gigawatts to terawatts, exceeding the total energy output of many countries. The infrastructure to generate and manage such energy, even for a brief pulse, would be extraordinary, and much of this energy would be wasted as the beam spreads. Increasing the sail's size could mitigate this issue, but a larger sail is heavier and more difficult to stabilize. The material for the sail must be exceptionally thin, nearly perfectly reflective, and capable of withstanding heat micrometeorites and the force of a powerful light beam. While advanced materials like graphene are suggested, none have been produced with the necessary scale or quality. A possible compromise involves smaller missions that use gram-scale payloads with miniaturized cameras, communication systems, and power sources. These chipsats would use sails a few meters in diameter, with the total mass being less than a candy bar. Sufficient laser power could accelerate them to high velocities, but communication over light-year distances would be challenging for a small transmitter, and the scientific instruments would be severely restricted. In the short term, this approach may be the most viable. Beamed propulsion is logical for rapidly sending a payload to another star, as it eliminates the need for onboard fuel, circumvents the risks of human spaceflight, and simplifies launches by leaving most hardware on Earth. The trade-off is the requirement for extreme precision in aiming, construction, and timing. The laser must be fired at a precise angle with precise power for a precise duration. While not impossible, these tasks are difficult. A laser powerful enough or an optic large enough for such a mission has never been constructed, nor has anything been guided with such accuracy over billions of kilometers. These challenges represent the limits of engineering and physics and could take decades or more to overcome. Even with solutions, these missions would not be for humans. The effectiveness of a solar sail depends on minimizing its mass. The sail material must be extremely thin, only a few microns thick and highly reflective. Materials such as aluminized mylar or captain have been utilized in test missions. In space, these sails are deployed and extended over large frames. A larger surface area allows the sail to capture more sunlight, generating a greater force for acceleration. Following deployment, the sail gradually gains velocity. In the vacuum of space, this acceleration is continuous, enabling a solar sail to increase its speed over months or years. However, the propulsive force diminishes as the distance from the Sun increases. The solar energy per square meter decreases with the square of the distance from the Sun. For instance, the pressure on a square meter of sail at Earth's orbit is approximately 9 micronewtons, but at Jupiter's orbit, it is only 1/25th of that amount. Near Pluto, the force is negligible. This factor restricts the applications of solar sails, which are most effective in the inner solar system where sunlight is abundant. Consequently, many proposed solar sail missions involve orbits near the Sun. Some concepts include an initial trajectory toward the Sun to capitalize on the more intense light, which provides stronger acceleration. By approaching the Sun closely, a sail can rapidly gain velocity and then use this momentum for travel to outer planets or interstellar space. Approaching the Sun is difficult, as the heat can damage a sail, warp its structure, or tear it apart. Materials that are effective in cooler space environments may not survive the Sun's thermal energy. Engineers must balance the advantages of high acceleration with the risks of thermal destruction. Due to these limitations, hybrid systems have been proposed. One concept involves starting with sunlight as the power source and switching to artificial light as the spacecraft moves farther from the Sun, which reintroduces the use of lasers. A laser array could provide high-powered light to the sail once the Sun's rays weaken. In this hybrid approach, the spacecraft starts its journey as a traditional solar sail, using natural light to gain speed. A laser would then take over perhaps past Mars or beyond Jupiter. By initially using solar power, the need for large amounts of artificial energy at launch is avoided. The laser array would be activated only when necessary, with its beam tailored to the sail's location. However, transitioning from sunlight to laser light is not a simple process. The sail must be engineered to reflect both types of light and aligned with great precision to capture the beam. The laser itself must also maintain a tight focus over vast distances. Another challenge is that solar sails have very low mass by design, which is beneficial for acceleration but detrimental to stability. These sails can be disrupted by micrometeoroids, slight changes in light pressure, or forces from the spacecraft's control systems. Some designs employ spin for stabilization, similar to a spinning top. Others use a shifting center of mass or adjustable control vanes for steering. These systems add complexity and elevate the risk of mechanical failure. Recovering a sail that has gone off course is difficult, as there are no brakes, and turning is not easily accomplished. Some advanced concepts envision sails that are kilometers wide, or networks of sails flying in formation to achieve higher speeds or transport heavier payloads. Building such structures would require time funding and new materials. Current efforts are focused on learning how to build small, reliable solar sails. The problem of weak sunlight in the outer solar system persists. A sail that performs well near Earth might become almost useless beyond Saturn. For deep space and interstellar missions, sunlight does not provide sufficient force, which is why laser-propelled versions are receiving more attention. With adequate investment, a laser array could transmit energy to a sail far beyond the sun's influence. This, however, shifts the problem to Earth and introduces political and environmental concerns. A laser powerful enough to propel a spacecraft at high speed could theoretically damage satellites or reach Earth's surface if misaligned, which concerns governments. While solar sails offer a quiet and steady method of space travel, they have limitations. They are slow, and their effectiveness diminishes with distance. Without a means to extend their range, such as lasers or other advanced technologies, they may be limited to local travel. Since the 1950s, fusion has been regarded as a technology that is perpetually a decade from realization. Fusion has long been an ideal solution, offering both high thrust and high efficiency. A fusion-powered spacecraft could traverse the solar system in months, with some designs suggesting travel to nearby stars within decades. For over 70 years, however, this has remained an unrealized goal. In the 1950s, scientists understood that controlling fusion reactions in space would provide a nearly perfect propulsion system. The fuel is light compact and energy dense, and the exhaust from a fusion reaction travels at extremely high speeds. This allows a fusion rocket to accelerate for longer periods and reach higher velocities without a heavy fuel load. Two primary methods have been proposed for initiating fusion on a spacecraft: magnetic confinement and inertial confinement, both derived from decades of fusion energy research on Earth. The magnetic approach is based on the tokamak concept, a toroidal chamber where magnetic fields contain hot plasma long enough for fusion to take place. Inertial confinement involves bombarding tiny fuel pellets with powerful lasers or particle beams to compress and heat them to the point of brief ignition. On Earth, both methods have advanced. Large-scale projects, like ITER in France, aim to demonstrate that magnetic confinement can generate more energy than it consumes. In the United States, the National Ignition Facility has achieved brief fusion reactions using high-energy lasers. Yet after decades of research and billions in funding, no reactor has produced sustained usable power. Controlling a fusion reaction requires containing plasma at temperatures exceeding 100 million degrees, which is hotter than the sun's core. As no solid material can withstand, this heat containment must be achieved indirectly through magnetic fields or momentary pulses of energy. The challenge is magnified when attempting to place this complex system inside a spacecraft. A terrestrial fusion reactor relies on massive support systems, including strong magnetic fields, cryogenic equipment, and intricate electronics. In space, access to large power plants or backup generators is not available. Everything must be self-contained and lightweight to initiate and sustain fusion. However, a large amount of initial energy is required. A second issue is heat management. Fusion reactions release significant energy as heat and radiation. On Earth, reactors can utilize cooling towers, thick radiation shielding, and heat exchangers. In space, heat must be radiated away slowly over large surface areas, which adds mass, complexity, and potential points of failure. Third, plasma containment within a moving and vibrating spacecraft is much less stable than in a fixed controlled facility on the ground. Magnetic fields can be disrupted by motion interference or temperature changes. Inertial fusion designs, which depend on precision lasers or particle beams, require perfect alignment and timing. A minuscule error of less than a millimeter or a nanosecond could cause the process to fail. Some early fusion rocket concepts attempted to address these problems. The Bussard ramjet from the 1960s proposed a spacecraft that would collect interstellar hydrogen with a large electromagnetic funnel and use it for fusion thrust. It was later determined that the density of hydrogen in space is insufficient for this design to work as required. Another concept was the magnetic mirror engine, which would expel plasma from the rear of the ship using magnetic nozzles. While this design showed potential, it also faced issues with instability and energy inefficiency. Most fusion experiments on Earth use deuterium and tritium, which are easier to ignite but produce harmful neutrons that degrade materials and create radioactive waste. A spacecraft becoming radioactive after a few months is undesirable. Consequently, researchers have investigated alternative fuels like helium-3, which are cleaner but more difficult to fuse and acquire. Another research area, magneto-inertial fusion, combines magnetic and inertial methods. These systems would compress plasma using rapidly moving magnetic fields or metal liners. While some of these concepts are being explored for terrestrial power, the designs are in early, unproven stages. The recurring projection that fusion is a decade away can be attributed to the fact that each breakthrough reveals new challenges. Achieving ignition, where the reaction produces more energy than it consumes, is not sufficient. The reaction must be sustained and controlled. Its energy converted into usable thrust, and the heat radiation and fuel supply must be managed. Each of these steps requires its own technology, and all must function together flawlessly. On a spacecraft, failure is fatal. A small leak, short circuit, or misalignment could disable the engine or lead to an uncontrolled reaction. Fusion, while clean in principle, is a volatile process. Despite these risks, fusion propulsion remains a highly attractive option for future space travel. Chemical rockets are approaching their physical limits, and ion drives are slow. Nuclear thermal engines represent an improvement, but fusion would be a significant leap forward. Private companies, military agencies, and international consortia continue to conduct experiments. Some startup companies claim they are close to developing compact fusion engines suitable for trucks or spacecraft. Some researchers are more cautious, focusing on achieving a proof of concept before discussing propulsion applications. Concurrently, scientists continue to make incremental progress in the underlying physics, including better magnetic confinement, more intelligent fuel handling, and new materials that can withstand neutron bombardment. The exact timeline for when fusion will become practical is unknown and subject to change, but interest remains strong due to the immense potential reward. A functional fusion drive would revolutionize space travel, enabling rapid trips to Mars, reducing travel time to the outer planets to months, and making it possible to reach another star within a human lifetime. Among all imagined propulsion concepts, none rivals the power of antimatter. It is considered the ultimate rocket fuel capable of unleashing energy with perfect efficiency through the contact between particles and their antiparticle counterparts. When matter and antimatter meet, they annihilate completely into pure energy, leaving no residue or spent fuel, only a massive release of radiation. In terms of energy per gram, this is the cleanest and most powerful reaction permitted by physics. The energy potential of antimatter surpasses all other sources. Even nuclear fusion is modest by comparison. The energy yield is substantial. 1 gram of antimatter reacting with 1 gram of matter releases approximately 90 terajoules of energy, which is roughly equivalent to the 21 kiloton explosive power of the bomb used on Nagasaki all from just 2 grams of material. Theoretically, a spacecraft carrying and safely converting a few kilograms of antimatter could traverse the solar system in days or reach the nearest stars within a fraction of a human lifespan. The resulting exhaust velocity would be immense, eliminating the need for oxidizers, heavy fuel tanks, or reliance on sunlight and gravity assists. However, this concept is far from reality. Although antimatter exists in nature and has been created in laboratories, its extreme scarcity and the difficulty of its production make the idea of fueling a spacecraft with it entirely theoretical. Antimatter is the mirror image of ordinary matter. The positron, the antiparticle of the electron, has the same mass but a positive charge. The antiproton, the antiparticle of the proton, has a negative charge. Combining an antiproton and a positron creates an anti-hydrogen atom. Scientists have produced anti-hydrogen in experiments trapping it for minutes in complex magnetic cages to study its properties. These experiments, however, involve only individual atoms, at most a few thousand or a few million. A functional rocket would require grams of antimatter. While this might seem achievable, current particle accelerators produce antiprotons in such tiny quantities that the total annual global output is measured in nanograms. At these rates, producing a single gram would take millions of years and cost more than the entire global GDP. The most optimistic cost estimates for antimatter are trillions of dollars per gram. The creation of antimatter involves colliding protons with targets at near-light speeds inside giant particle accelerators. These collisions generate showers of particles, including a very small number of antiprotons that must be collected, slowed, cooled, and stored. Each step of this process loses particles, resulting in extremely low overall efficiency. For every million protons collided, only about 1 usable antiproton might be produced. The equipment required for this process is massive, power-intensive, and incredibly delicate. Even if production efficiency could be improved and costs reduced, the challenge of storage remains. Antimatter annihilates upon contact with any matter, including container walls, air, or even a speck of dust. Therefore, it cannot be stored in a tank or as a pellet, but must be suspended by electromagnetic fields inside a perfect vacuum, isolated from all physical contact. This has been achieved on a microscopic scale with devices like the penning trap, which uses a combination of electric and magnetic fields to suspend charged particles. Physicists at CERN have used this device to trap antiprotons and combine them with positrons to form antihydrogen atoms. However, storing grams of antimatter would require magnetic containment systems far more stable and reliable than anything ever built, and they would need to operate flawlessly for years. Any malfunction, power loss, or physical breach would cause an instantaneous catastrophic explosion. Antimatter particles must be slowed and kept at cryogenic temperatures to remain trapped, which adds complexity and potential points of failure. In space, where extreme temperatures already pose significant engineering challenges, implementing a cryogenic high-voltage magnetic containment system for a substance that would vaporize the ship upon the slightest mishandling is an enormous burden. Some spacecraft designs attempt to bypass this problem by using small doses of antimatter to ignite fusion reactions or heat conventional propellants rather than storing large amounts. One proposal, an antimatter-catalyzed microfission fusion engine, involves injecting antiprotons into small pellets of nuclear material to trigger a miniature explosion that drives a standard rocket nozzle. While this reduces the amount of antimatter required, it still necessitates stable storage and precision delivery of antiprotons capabilities that have not been developed at scale. Other more speculative concepts suggest collecting natural antimatter trapped in Earth's magnetic field or from the belts around gas giants like Jupiter. Although evidence suggests trace amounts of antimatter exist in these regions, its density is so low that gathering even micrograms would require giant collection surfaces and long-time frames. Another idea is the construction of space-based antimatter factories, vast solar-powered accelerators orbiting the moon or sun to continuously synthesize antimatter. While technically possible, such projects would require an infrastructure and investment level far beyond anything built to date, comparable to building a Saturn V rocket every week for decades with no immediate return. There is also a military concern. A few milligrams of antimatter can create explosions larger than conventional bombs, and grams would rival small nuclear weapons. Any nation that could produce, store, and control antimatter would possess unprecedented destructive power, making it a political and security risk as well as a scientific challenge. Despite these difficulties, antimatter research continues to progress slowly. Experiments at CERN and other labs are providing more information about antimatter's behavior, leading to the design of better traps and plans for new accelerators. In the distant future, if costs can be reduced and containment made reliable, antimatter might play a role, perhaps not in full-scale engines, but in triggering high-efficiency reactions or in compact high-thrust stages for deep space missions. For now, the gap between what is possible in a laboratory and what is needed for a working propulsion system remains vast. The energy is available, but the means to harness it are still unresolved. First proposed in 1994 by theoretical physicist Miguel Alcubierre. The Alcubierre drive offers a theoretical loophole in Einstein's general theory of relativity. Instead of moving a spacecraft through space by conventional means such as rockets, this concept suggests bending space-time itself. The ship does not move in the traditional sense. It remains stationary within a bubble, while the space in front of it contracts and the space behind it expands. The ship rides this distortion like a surfer on a wave, moving through the universe without ever locally exceeding the speed of light. At first, this seems impossible, as Einstein's equations prohibit any object with mass from traveling faster than light. As an object accelerates toward light speed, its mass increases, and the energy required to continue pushing it rises dramatically, becoming infinite at light speed. However, general relativity does not place a speed limit on the expansion or contraction of space itself. The early universe expanded faster than light during inflation. The Alcubierre drive exploits this by moving space around the ship, rather than pushing the ship through space. The complex mathematics behind this idea involve a warp bubble, a region of flat space-time where the ship sits surrounded by a shell of twisted geometry. In front of the bubble, space is compressed, and behind it, space is stretched. As this entire region moves forward, the ship is carried with it, despite never actually moving from its own point of view. The Alcubierre drive is not a form of reactionless propulsion. Unlike discredited concepts such as the EM drive or other fringe ideas, those concepts purport to propel a craft without ejecting mass or interacting with an external medium, which violates the principle of momentum conservation. The Alcubierre drive does not violate momentum laws and operates through a different mechanism. The system does not push the ship forward. Rather, it modifies the shape of the space in which the ship is situated, which is a key distinction. The concept is theoretically consistent with general relativity, but its energy requirements are impractical. The equations for creating the necessary space-time curvature for a warp bubble require what is known as exotic matter, which has a negative energy density. This material would effectively possess negative mass repelling gravity instead of attracting it, while normal mass curves space inward. Exotic matter would curve it outward. Quantum theory indicates that effects like the Casimir effect involve a form of negative energy in a limited and transient sense. In this effect, two metal plates in close proximity within a vacuum experience an attractive force caused by the suppression of vacuum fluctuations between them, suggesting the energy in that region is negative relative to the surrounding space. However, this is a minuscule effect measured in nanograms. To bend space sufficiently for a ship to travel within a warp bubble, a vast quantity of negative energy would be needed, several orders of magnitude greater. Early calculations for a functional Alcubierre drive suggested a requirement for more exotic matter, mass energy than exists in the observable universe. Subsequent refinements reduced this estimate to the mass of Jupiter or even a few thousand kilograms. These lower figures, however, still rely on a type of exotic matter that has never been produced or confirmed, and they are based on idealized geometries and simplifications that might not be applicable in real-world physics. A warp bubble, once created, might be unstable. Simulations indicate it could collapse or release destructive radiation during activation or deactivation. There are also concerns about how a ship inside the bubble would interact with the external universe, because the bubble would move faster than light. Relative to the surrounding space, no signal could penetrate its forward edge. This would leave the ship causally disconnected from the universe ahead, meaning the crew could not steer, brake, or communicate until the journey's end, when the geometry returned to normal. Another potential issue is the creation of extreme tidal forces. Similar to how an object falling into a black hole is stretched and compressed, a poorly formed warp bubble could tear apart its contents. While some solutions to mitigate these tidal effects have been proposed, they depend on the precise engineering of exotic matter, assuming it can be created at all. There are also practical safety concerns. Particles from the interstellar medium might accumulate at the front of the bubble, similar to debris on a bow wave. Upon the bubble's collapse at the destination, this accumulated energy and matter would be released in a concentrated burst, potentially destroying the target area. This wake effect could render the drive unsafe. Even if it were possible to construct the Alcubierre drive, is an intriguing theoretical solution to the equations of general relativity under highly unrealistic conditions, showing that faster-than-light travel is not strictly forbidden if space itself can be manipulated. However, transitioning this concept into a functional technology would necessitate breakthroughs in quantum field theory, materials, science, energy generation, and containment that are not yet defined. Researchers are exploring modifications to the original concept to enhance its plausibility. Proposals include warp geometries that reduce the need for exotic matter by reshaping the bubble, as well as designs for drives that travel at subluminal speeds while using space-time manipulation to decrease travel time. These speculative approaches aim for more reasonable energy budgets and may offer testable predictions in the future. For now, the Alcubierre drive remains a glimpse of what might be possible, not a blueprint for a working technology. For interstellar voyages using conventional propulsion, two main mission concepts are considered. One is a small, long-duration crew of a few dozen people supported by advanced AI and automation. The other is a generation ship, a large, self-sufficient world with hundreds or thousands of inhabitants whose distant descendants would reach the destination. Each model presents unique psychological challenges. In a small crew scenario, isolation is extreme. Even on 6-month missions aboard the International Space Station, astronauts experience significant mental strain due to their separation from Earth's natural rhythms and limited social environment where minor irritations can escalate. On a voyage lasting 10,000 years or more, this isolation would become vastly more complex. The possibility of returning home would be non-existent, as Earth would have changed beyond recognition. Long before the mission's midpoint, a small crew would become a closed social, emotional, and cultural system. Communication from Earth would face increasing delays, with a single radio signal taking over 4 years to reach the nearest star systems. After several centuries, messages from a society the crew could no longer relate to would become meaningless before ceasing entirely. The psychological impact of being confined to a spacecraft with only machinery, sounds, and a few other voices is a significant concern for a mind evolved for life on Earth. Studies of confinement in environments like Antarctic stations and submarines show that long-term isolation can lead to depression, disrupted sleep, increased irritability, and emotional blunting. Individuals may withdraw even with recreational facilities, and communication time perception can become unstructured, and events may feel repetitive, making mental health fragile. These effects could be amplified on a centuries-long mission. While automation might reduce workloads, it could also decrease stimulation, making boredom a persistent danger. The lack of new challenges and stimuli can lead to sensory monotony, affecting cognition, mood, and memory. The alternative concept. The generation ship involves a large population on a one-way journey, living, reproducing, and dying on board for many generations. This model avoids the need for suspended animation or prolonged boredom by accepting that the original crew will not see the destination. Culturally, the generation ship is in some ways more realistic, as its inhabitants would be living their lives rather than waiting. The ship would be their world, complete with its own schools, families, traditions, and independent social systems. However, this model presents its own challenges. Identity is a major concern. The first few generations might be raised with knowledge of Earth, but after several hundred years, it would become an abstract concept or a myth. Individuals born on the ship would see themselves as citizens of a sealed world, not passengers. The destination itself would be similarly mythical to those living during the long middle period of the journey. This could lead to a decline in motivation and cultural drift, potentially resulting in apathy or resistance toward the mission. Over many generations, belief systems could change, and factions might emerge that wish to turn the ship around or abandon the mission, viewing it as irrelevant to their lives. We'll end it off right there. Thank you guys so much for watching this documentary. Be sure to like this video